Good afternoon, students. From the last lecture, we are talking about the second series of inner transition elements called actinoids. That is the second series of block elements. There are the total 14 elements present in actinoids. There is the last topic of last lecture, properties of actinoids. There is the last property of actinoids, oxidation states. There are total 3 electrons present in the valence of actinoids. See here, there is the availability of valence electrons of actinoids in 5s, 6d and 7s. There are total 3 electrons present in 6d and 7s. So actinoids showing the common oxidation state +3. But there is also the availability of electrons in 5f orbitals. So actinoids having a tendency to show the variable oxidation state from +3 to +7. Right? That have a tendency to show the variable oxidation states. But lanthanoid does not showing the variable oxidation state. That actinoids have a tendency to show the variable oxidation state, because all these 3 valence orbitals, they are much closer to one another. There is a shifting of electrons takes place from one orbital to the other. Then there is the next point of this lecture, applications of actinoids. There are some applications of actinoids. In the last lecture, I am already telling the isotopes of thorium 232 and uranium 238 and uranium 238. Their half-life periods are so long that we get very negligible radiations from these elements. So we find them in everyday use, like the television color tubes. They are used. For example, thorium 4 oxide, THO2. This thorium 4 oxide mixed with 1% of cerium oxide, and this mixture was used as a major source of indoor lighting. Before incandescent lamps came into existence, only because these oxides converts the heat energy from burning natural gas to an intense light. Even today, there is a great demand for these lights for outdoor camping. This is the application of thorium 4 oxide. Then there is another actinoid, uranium. That uranium also having the application in nuclear reactor. Uranium is the another actinoid that is in great demand as used in nuclear reactor. But this uranium, how this uranium is extracted from the ore? The extraction of uranium showing the interesting chemistry. The ore of uranium 4 oxide, that is UO2. This uranium oxide is treated with iron 3 iron to form uranium 6 oxide, UO3. That uranium 4 oxide converted to uranium 6 oxide on treating with iron 3 iron. And that reaction is UO2 in solid state plus water in liquid because you take the aqueous solution of iron 3 plus to form uranium 6 oxide plus 2H plus ions plus 2 electrons. And in this reaction, that iron 3 plus converted to iron 2 plus, that is Fe2 plus. That is the first step. Uranium 4 oxide converted to the uranium 6 oxide. Then there is the second step. In that second step, there is the addition of H2SO4 in this solution to produce uranyl sulfate. This uranyl sulfate contains UO2 2 plus ion. In first step, after the formation of uranium 6 oxide, there is the addition of sulfuric acid to form uranyl sulfate, and reaction is UO3 plus H2SO4. UO3 plus H2SO4 to form uranyl oxide UO2 SO4 plus H2 plus H2. Right? That uranyl sulfate contains this ion UO2 2 plus ions. Here this is the second step. Then after the purification of uranium, ammonia is added to the solution to give yellow precipitate of ammonium diuranate. Right? After the purification, from this, if you want to collect the uranium, then separate and take the uranium. But after the purification of this uranyl sulfate, that ammonia is added to the solution to form ammonium diuranate, and this yellow precipitate of ammonium diuranate having the wide application, right, in the form of uranium. Then that step, that uranyl sulfate treated with ammonia. There is the 6 molecules of ammonia, that also aqueous plus 3 water molecules thrice H2O to form ammonium diuranate, that is NH4 twice Q7O7 plus twice ammonium sulfate. That is in solid state and this is in aqueous state. Clear? And this ammonium diuranate is used in form of uranium. This is the application of uranium. Clear? That are the complete applications of actinoids. Then there is the next topic. There are the 2 series of inert transition element. The first series is lanthanoids and second series is the actinoids. There are some similarities between these 2 series and there are some difference between these 2 series. First we are talking about the similarities of lanthanoids and actinoids. Okay? Then first, which are the similarities between both? There is the first similarity. There is total 3 electrons in the valence of both in d orbital and the s orbital. So, both series elements show the common oxidation state +3. Both the series show +3 oxidation state. Then second similarity, in both lanthanoids and actinoids. F orbital fill gradually. F orbital fill gradually. Right? For the lanthanoid, there is the filling of 4f orbital, and for the actinoid, there is the filling of 5f orbital. That is 4f series, and second is 5f series. Then the third similarity. For both lanthanoids and the actinoids, both are present in a period, and according to the period, they have the one similarity. Their ionic radii in +3 oxidation states gradually decreases with increase in atomic number. Ionic radii decreases with increase in atomic number. Then the next similarity, the elements of both series having low electronegativity. The elements of both series having low electronegativity and are said to be highly reactive. This is the similarity between both series elements. Then the next similarity, the nitrates, perchlorates and the sulfates. The nitrates, perchlorates and sulfates of lanthanoids and actinoids are soluble. These are the solubles, but hydroxides, fluorides and carbonates are insoluble. These are the similarities of lanthanoids and actinoids. Nitrates, perchlorates and sulfates are easily soluble, but hydroxides, fluorides and carbonates are not soluble. They are insoluble. These are some similar points between lanthanoids and the actinoids. Clear? Then there is a difference between lanthanoids and the actinoids. There is a 3 marks question asking on this difference. Distinguish between lanthanoid and actinoids. Then you write minimum 6 points for the distinguish. See, distinguish between lanthanoid and actinoid. There are the many point of difference between both. There is the first difference, the position of lanthanoid and the position of actinoids. The position of lanthanoid is 3rd group and period 6, and actinoids 3rd group and 7th period after the actinoid. Right? Then second difference, for the lanthanides, the valence electrons enter into 4s orbital. There is the filling of electrons takes place in 4f orbital, and here there is the valence electrons present in 5f orbital. So lanthanoids are called the 4f series elements and actinoids are called the 5f series elements. Then third, their elements. That lanthanoids started with lanthanum, or you say cerium 58 to lutetium 71, and actinoids started with actinum, then thorium 90 to lawrencium 103. Then there is the next difference. Their general electronic configurations. Their general electronic configuration. For lanthanoids, you write xenon core, then 4s 0 to 14, 5d 0 to 1, 5d 0 to 1, 6s2. And for actinoids, you write radon core, 5f 0 to 14, 6d 0 to 2, 7s2. 0 to 2, 7s2. That is the difference. The next point of difference, except promenthum in lanthanoids, all are non-radioactive. Except promenthum, all are non-radioactive. Right? Because promenthum is not the naturally occurring compound, but the remaining elements of lanthanoids, they are naturally occur. But actinoids are all synthesized in lab. They are the man-made elements. So all are radioactive. These actinoids are prepared during the nuclear reactions. They are synthesized in lab, so they are all radioactive. Next, the lanthanoid showing the maximum oxidation state +4. Maximum oxidation state +4. Or you say lanthanoid showing the limited oxidation states +2, +3 and +4. But the actinoid showing the variable oxidation states +3, +4, +5, +6 and +7. This is the difference. Actinoid showing the variable oxidation states. The next one, lanthanoids do not form complexes. They do not form complexes because of the limited oxidation states, and actinoids forms the complexes because of the variable oxidation states. Then next, lanthanoids do not form oxocation. They do not form oxocation, but actinoids form oxocation. There is the one-two example of oxocation of actinoid from uranium, UO plus, then plutonium, that also forms the oxocation, PuO plus. Then there is a last difference. The lanthanoid contraction is less. Lanthanoid contraction is less as compared to actinoid contraction, and actinoid contraction is more as compared to lanthanoid contraction. What is lanthanoid and actinoid contraction? There is a gradual decrease in ionic and atomic radii with increase in atomic number, and this is a more as compared to the lanthanoids. These are the difference between lanthanoids and the actinoids. Then there is the next point given in textbook. There are some point of similarity and difference between pre-transition metals, lanthanoids and transition metals. pre-transition metal. Lanthanoid, and here is the transition metal. There are some point of difference between these three and similarity between these three given in one table, that is here. Then first, you know the lanthanoids. There is a first series of block elements started from cerium to lutetium. These elements are followed by the lanthanum. And this lanthanum is placed in D block element. There is the first element of third series of D block. Then what is the pre-transition metals? Pre-transition metals means the elements present in group number 1 and group number 2. And transition metals means the elements of D block elements. And these lanthanoids are placed in between the transition elements. Okay? So these are called the inner transition elements. Then see, there is a first point oxidation states of these. Then first group number 1 and group number 2. That means they show the N plus oxidation state. They show the N plus oxidation state. Generally, the three transition elements group number 1 are monovalent, but there is a group number 2 that show the N plus oxidation state, that is 1 plus and 2 plus. Then second, lanthanoid showing the common oxidation state plus 3. Beside the plus 3, they show plus 2 and plus 4. Then transition elements. There is the availability of electrons present in d orbital, so transition element showing the variable oxidation state. Variable oxidation state. Then next point, all these elements are compared according to the periods. The periodic trend by effective nuclear charge and noble gas configuration. For pre-transition metal, the periodic trends by effective nuclear charge and noble gas configuration. And noble gas configuration. The next one, this lanthanoid showing the lanthanoid contraction. Their ionic radii goes on decreasing with increase in atomic number. That is lanthanoid contraction of Ln3 plus ion. Then for the transition metal, their size changes. That is atomic size or ionic size changes because of the variable oxidation states. There is the next one. This pre-transition metal showing the similar property for group. They showing the similar property for group. According to the group number 1, they show the similar. According to the group number 2, they show the similar. That lanthanoids also showing the similar properties. But for the transition metals, they show the substantial changes in property. They show the substantial changes in property. Right? That pre-transition metals, They are the metals. So they are always hard. Right? Similar for the lanthanoids. For pre-transition metal and the lanthanoids, that are also the hard. Always hard. And for the transition metals, they are the heavier elements. Their melting point and boiling points are very, very high. There is a next point. No ligand field effect. No ligand field effect. Pre-transition metals show only the one oxidation state, +1 for group 1 and +2 for the group 2. They show the no ligand field effect. For the lanthanoids, there is the insignificant ligand field effect. And for the transition metals, they having the ligand filled metal because of the variable oxidation state, that is substantial. That is substantial ligand filled effect of transition metal. There is a next one. Poor coordination property for pre-transition metal. Poor coordination property. The lanthanoid showing the high coordination property, and transition elements coordination number is 6. Coordination number is 6 is typically maximum. It is the typically maximum. Right? Then next, for the pre-transition metal, there is a flexibility in geometry. That pre-transition metals, lanthanoids and transition metals reacted with the compounds, reacted with the other elements to form the compounds, and there is a flexibility in the geometry for pre-transition elements. Flexibility in geometry. For lanthanoids, that is also same, flexibility in geometry. But for the transition element, they show the fixed geometry. They showing the fixed geometry. They showing the fixed geometry. And there is a large point between these three pre-transition metals. There is no magnetism. There is no magnetism. They show the magnetism. Lanthanoid showing the magnetism. We are talking the property of lanthanoids, magnetic property. Then same actinoids also showing the magnetism. Clear? These are the point of difference and point of similarity between these three, or you say you're talking about the two groups. Clear? Then there is a last point from this chapter, post-actinoids. Post-actinoid elements. See here. Which are the post-actinoid elements? You have already seen that the elements having the atomic number greater than 92. The elements with atomic number greater than 92 are called the transuranic elements, or they are called the transuranium. Then the elements from 93 to 103. 92 to 103, they are included in the actinoids. These elements are the actinoids. Right? The elements greater than 92 are called the transuranic elements. Then the elements from 92 to 103 that are included in the actinoids. But the elements from 104 to 118, these elements are called the post-actinoids. They are called the post-actinoids. They belongs to the transition elements. Some of these elements belongs to the transition elements. These post-actinoids show the similarity with actinoids. They showing some property similar with the actinoids. They can be synthesized during the nuclear reaction. These post-actinoids are also synthesized during nuclear reaction. During nuclear reaction. There are total 9 elements. They are synthesized during nuclear reactions. It is difficult. It is very difficult to study their chemistry because the isotopes of these elements are very short-lived. Their half-life periods of isotopes of these post-actinoids are very short-lived. For example, the element with atomic number 112 that having the half-life period of 2.8 into 10 raised to minus 4 seconds. That means there is a milliseconds. These are the milliseconds. That means very short-lived. Out of this, that Rutherfordium, out of this post-actinoids, Rutherfordium forms the chloride. Rutherfordium forms the chloride that reacted with the chlorine to form the chloride RfCl4. This property show the similar with zirconium and hafnium. This is the similar property of Rutherfordium with zirconium and hafnium in +4 oxidation state. In +4 oxidation state. Then there is another element, dubnium. The post-actinoid element dubnium that resembles to both. That resembles to both. First, group number 5. That dubnium resembles the one element of group number 5 named niobium. Niobium 5. Niobium 5. And also resembles with the actinoid. Out of this actinoid that resembles with the protactinium. Protactinium 5. That show the similar property with the actinoids. So these elements from the atomic number 104 to 8, that is 118 in modern periodic table, they are called the post-actinoids. They are followed after the actinoids. Clear?